Hi, and welcome back. Today we're going to start chapter 11, which is about momentum and impulse. We're going to study multiple particles now, and if you remember, up to this point, through chapter 10, all the objects we have studied were point particles. They did not have a shape, they did not have an orientation. We just had objects that were just one particle pretty much. Or point particles. Now we're setting the stage to study multiple particles, and objects will earn themselves a shape and could have an orientation. So in the next chapter, which is rotational motion, we're going to look at objects that will start rotating. All right, let's do that. So, of course, we're going to start with a definition. So here's the definition. Momentum has the symbol P, and it is defined as the mass of the object times its velocity. Why is it defined this way? Well, that's the way it is defined. And you can define anything you like. Again, definitions are neither right nor wrong. It's whether they are useful or not. In this case, they are useful. And the reason we define momentum this way is because it's related to the force. And I think I've mentioned this already early on when we did Newton's laws. So first, the units for momentum are, it's kilogram meters per second. So kilogram meters per second. Newton's second law. So the second law. We mentioned that a while ago that the net force on an object, was actually formulated according to Newton himself as the rate of change of momentum, dp dt. And if you take this derivative, you will have d dt of mv. If the mass is not changing, it comes out, and you just have the mass times dv dt, which is a, the acceleration. So this is the more general form of Newton's second law, or this. From here to here, it's a specific case where the mass is constant. We're going to talk about, toward the end of this chapter, the motion of a rocket as it goes up. Its mass will significantly change, and so the mass is no longer constant, and so we will have to be careful with this term here, as we will see. That's the second law. So let's go here. From now on, I'm not going to write F net, because it's understood when you say F equal to ma or F equal to dp dt, you mean the net force on an object, the net external force on an object. Right? You apply a force on an object, that's what we mean. So we would have this. Then we have dp dt is equal to F. And so dp dt, the differential dp, will be F dt. And if we integrate both sides from the T initial to T final, and on here, what is this quantity called? This will be called F dt here, is called J. And it is known as the impulse. F dt is the impulse. How much is it? Well, you have to integrate this. If you're given the force and time, then you have to perform this integral. However, if you're given the change in momentum, you can calculate it by just integrating dp. It will be p from p initial to p final. So it's the change in momentum, p final minus p initial. And I dropped my vector sign. So that is the impulse. So the impulse, compared to, let me write it this way. The impulse is the integral of f dt from t initial to t final. Let's say you push an object for a certain amount of time, you have given it an impulse. Remember with the work, W, the work done, this is the change in momentum. Remember the work done was the integral of f dx, f dx from x initial to some x final. That was, you apply a force over a certain distance. Here we're applying a force for a certain length of time. When you integrate the force with respect to time, you get the change in momentum, which is called the impulse. When you integrate the force with respect to position, you get the work done, and the work done, if you remember, was equal to the change in kinetic energy, delta K. Delta K. So by kind of similar to each other, all right? So let's do an example of this. It says here, a baseball is thrown with a speed of 20 meters per second. And then it is hit straight back toward the pitcher. So here is a person. The person is here, and that person throws a ball. So that ball comes this way, and then it hits a bat, a baseball bat. How do I draw a bat like this? So it hits the bat with 20 meters per second. So this is before, right before it hits the bat, and this is after it hits the bat. After, the pitcher, the person who threw the ball, is still there, and here is the baseball bat, the bat. That's not a very nice bat, but you get the idea. The ball hits, then bounces back toward the pitcher, and then it is hit at 40 meters per second. 40 meters per second. So it says a 150-gram baseball is thrown with a speed of 20 meters per second. It is hit straight back toward the pitcher at a speed of 40 meters per second. So at first it was moving left, and now it's moving right. If you like, you can flip them. The pitcher is here, so at first the ball will go right and then go back left. So once you choose directions, just commit to them. I'm going to just commit to this here. It doesn't matter that. Here is my positive x direction. Positive x direction. So now, they say the force when the baseball bat hits the ball, this is the force versus time. This is how it looks like. So this is before the ball hit. So the force is 0. You can't apply a force to the ball before hitting the ball. Now once the ball hits the bat, as you see, the ball collides with the bat, and the ball kind of deforms a little bit. And when it has maximum deformation, this is basically the highest force you apply. And then the force starts to turn back and leave the bat and go back. And that's when it starts to lose contact with the baseball bat. Once it loses contact, the force drops to 0 because it's no longer touching, so there is no more force. So this is how the force looks like, basically. I mean, they're giving us this. I mean, the force typically might look something like that. You have to, the exact shape of the curve usually is more complicated than this, and you have to use like a really fast camera to look at the shape of the ball, and they have those, and then figure out how the shape of the curve maybe looks like, determine it. Or use like force sensors. There are force sensors that tell you how much force you're applying at this moment. So as soon as the baseball hits the bat, the force sensor will give you force readings, and then it will give you some kind of a shape, and then usually maybe the shape looks like this. Anyways, somebody collected the data and gave us this. We're concerned with the baseball bat's motion along the x direction. So in the x direction, there is only the bat hitting the ball. Yes, there is gravity, but that's downward. I want the x direction of the force. And so this is it. So they say calculate F max. How are we going to even do this? How are we going to calculate it? Well, it's the chapter of momentum, and it says that the change in momentum, let me write change in momentum. Since we're talking about the momentum in the x direction, I've just put that like this. Change in momentum. I will not put the vector signs because we're just in the x direction. would be the integral of f dt from t initial to t final. I know the change in momentum. Right before the ball hits the bat, it had some momentum, and then after hitting the bat, it has a different momentum. Well, before it hits the bat, the momentum was mass times velocity. Because remember, by definition, momentum is mass times velocity. And remember, and it's a vector. Momentum is a vector. If you're talking just in one dimension, it's enough to say use plus and minus signs. But if you're talking in two dimensions, you have to use I hat and j hat. We're talking about one dimension here. So I'm going to say that the initial momentum, P initial, it's in the x direction, and it's the mass times the velocity at the beginning. It's the mass times the velocity at the beginning. The mass of the baseball is constant. It's 150 grams. So I would write 150 grams, which is 0.15 kilograms, times V initial. The ball is moving this way. It shows the left side to be negative. If you chose a different commitment, you will get different signs, but at the end, the magnitudes will all be the same. So let's stick to this. So it would be minus 20. And so multiply these two, you will get, I will not what, like 3, I think? But let's just do it. 20 times 0.15, that's 3, with a minus sign. So it's minus 3 kilogram meters per second. And then P final will be the mass times V final. The mass is still 0.15. The final velocity was 40 meters per second to the right. So it's 40. Positive 40 because it's to the right. So when you do this, you get positive 6 kilogram meters per second. That means the change in momentum will be the final momentum minus the initial momentum. The final momentum is 6 and the initial momentum is minus 3. And so you will get 6 minus 3, that's positive 9 kilogram meters per second. That's delta P. So I know the left side. Now how about the right hand side here? How am I going to do this? Well, remember the integral pictorially is calculating the area under the curve. And we have this curve here. We're integrating force versus time, so that's the force, that's the time. So it would be the area of this. So what's the area of this triangle? Well, it's half the base times the height. So this part here will be half the base times the height. The base is 3, and the time here is milliseconds. Because remember, when you hit the ball, it will not last for 3 seconds. It will be very quick. It will hit and come back. So that's apparently about 3 milliseconds. That's a reasonable number. So 3 milliseconds, that's the base. But 3 milliseconds is 3 times 10 to the minus 3. Milli is 10 to the minus 3. And then the force itself is F max. I don't know what this height is. So it will just be F max. Just keep it that way. F max. And now, we know the left-hand side, it's 9. And the right-hand side is this with only one unknown, F max. So that's relative. So the left-hand side is the 9. And then the right-hand side is the 1/2 of 3 times 10 to the minus 3 F max. Well, if you could simplify this, 9 over 3 is 3 on the left side. You multiply by 2, you get 2. And then multiply by 1,000, you get 2,000. So the force will be about F max will be 2,000 newtons. Let me just double check my work. Yeah, I'm sorry. Did I say it should be 6,000? Yeah, 6,000. 6,000 newtons. So that is the force. Okay. So that was the average force. If you want the, I'm sorry, that was the maximum force. What's the average force? I mean, the average force is somewhere between, well, it was 0 and a maximum value of 6,000. So what's the average force? Well, we can write the average force as the average force on average. It's the change in momentum over the change in time. And the momentum changed by 9, that's delta P. And then the time is, it made that change over a 3 millisecond period. That's 3 times 10 to the minus 3. And if you do 9 over 3 is 3, and 1 over 10 to the minus 3 is 1,000. So 3,000 newtons. That's on average what the force is. It's not 6. The maximum force was 6,000, and the average is 3,000. All right. Okay, so great. And now we have this thing, and it seems like we just have Newton's law, second law, all over, and there is no use for this. So what do we? Why are we even defining momentum? The reason is because it's a useful quantity, and we're going to use it with collisions and when we do conservation of momentum. So let's take a look at this conservation of momentum concept. Conservation of momentum. Conservation means it's constant. The momentum before is equal to the momentum after, provided that you satisfy certain conditions. So let's start with one particle by itself. Again, we know that the net force on an object is equal to the rate of change of its momentum. So if you just have one object, if the net external force on that object is equal to 0, if the left-hand side is 0, so if, let me just to emphasize the net external force, the net external, I'll put external here, the net external force. If F external is equal to 0, that means dP dt is equal to 0. And if you take the derivative of a quantity and you get 0, it means that that quantity is constant, right? Because the derivative of a constant is 0. It means that P is constant. That's what it means in terms of one object. So if you look at an object and to figure out whether or not its momentum is conserved, you say, is there an external force on the object? If there is, then it's not conserved. If there isn't, if the net external force is 0, then it is conserved. Now, how about if I have two objects? Let's say here is object 1, M1, and it will be moving at speed or velocity, let's say velocity, V1. And then here is M2, and it's moving with velocity V2. And let me call it V1 initial, because they're going to collide. And this is V2 initial. They're going to come together and collide. They're going to collide. And then after the collision, they will depart from each other. M1 might move this way with V2 final. And then M2, I'm sorry, this is M2 to the right, so this is M2, and this is M1 might depart this way. I say might because after the collision, if this is so heavy compared to this one, it's like a wall, this one will this will bounce back and this one will continue. We'll figure out when that happens, but let's say for now, V1 final is in maybe this direction. Okay? So after the collision, before the collision, and during the collision. This is before, during, and after. So during the collision, the net external force on M1 is not 0 because it collided with M2. So M2 applied the force on M1. And then the net external force on M2 is not zero because M1 applied an external force on M2. Because if you, by Newton's third law, if M2 applies a force on M1, then M1 applies a force on M2, and it's a contact force, basically a normal force. So M2 experiences a force this way. I will call it the force on M2 due to M1. M1 experiences a force that's this way, and that's the force on M1 due to M2. I just use it this way. This is my notation. The force on 1 due to 2. The force on 2 due to 1. On by. On 1 by 2. On 2 by 1. So the first one is on who, and this one is by who. So this is the force on 1 due to 2. The force on 2 due to 1. So let's write down the momentum equation for mass 1 and then the momentum equation for mass 2. So the change in momentum, let me write it this way. dP for mass 1 dt is equal to the force on object 1. The force on object 1. But on object 1, let's say there is only one force. We're on outer space. Forget about gravity, friction, and so on. We will add them later. Suppose now, in existence in this universe, you only have these two masses and they're colliding with each other. The only force on M1 is the force on 1 due to 2. Due to 2. And then, let's look at mass 2. Newton's second law says the net external force on an object, since we're talking about object 2, the force on object 2 due to object 1, the force on 2 due to 1, is equal to the rate of change of momentum for M2, dP dt. That's Newton's second law. Right. You probably will guess, what am I going to do with these two equations? F12, F21, they're begging you to add them together. So we're going to add them together. Let's add these two together. What do we get? On the right-hand side, you will get, actually, let me add the left side first. I get dP1 dt plus dP2 dt is equal to F12 plus F21, right? Okay, what do we know about F12 plus F21? The force on 1 due to 2 plus the force on 2 due to 1. They are equal and opposite by Newton's third law. We're always guaranteed that F12 is equal to negative F21. So when we add these two, we will get 0. We'll get 0. So the right-hand side, you will have 0. On the left side, I'm going to collect these. So this is d dt of P1 plus P2. P1 plus P2. Okay? And what is P1 plus P2? It is the total momentum of these two objects added together. So, this is the total momentum. dP dt is equal to 0. So what this is saying, the total momentum of these two objects added together, P1 plus P2, will be conserved, will be constant, meaning the momentum before collision, total momentum before collision, will equal to the total momentum after the collision, provided that you include all the momentum of all the interacting particles, in this case M1 and M2. How about if you have 3 masses or 4 masses or 20, you will do a similar analysis like this. If you have 3 masses and they're colliding together, then on mass 1 there will be the force from mass 2 on 1 plus the force on 1 due to 3, and you add them together, and then you will have like 3 equations, and when you add them, so you basically, the book does it, they use summation notation, and then you will get the rate of change of the total momentum is also equal to 0, provided that you include in your system all the forces that are internal, because these are called internal forces when they collide. So if I take mass 1 by itself, then the force on mass 1 due to mass 2, that's external to M1. and the force on 2 due to 1 is external to M2. But if my system consists of these two masses combined together, then the fact that M1 pushes on M2 and M2 pushes on M1, that's an internal force, and Newton's third law says those internal forces are going to cancel, and the total momentum will just be constant. Notice, no one is saying that the momentum of M1 individually doesn't change, or the momentum of M2 individually does not change. In fact, they do, and that is the case. They do change, but the change happens so that when you add the total momentum of this one before and the total momentum of the two added together afterwards, that momentum in total will be constant. Meaning, sure, M1 might lose some momentum, might decrease, and M2 might gain, but the loss of M1 will be the gain of M2, or vice versa. Okay, I'm going to pause this, and then we will do an example on conservation of momentum, and we will go on.